Yeah, so as Ray said, I'm Kirsty. I'm currently an associate professor based at the University of Birmingham. And I trained I fell in love with geology as a young child, and it's kind of stuck with me ever since. And I trained as a marine micropaleontologist. So I've been to sea multiple times on various ocean-going vessels. And you can see an image of me sort of spending 2 months down in the Southern Ocean, testing out my survival suit there whilst working on the microscope. And I'm really interested in what past life, well, in what past life did, and what it can tell us about what past worlds looked like, so how it can be applied. And my specific sort of area of interest really is in how past high CO2 worlds actually worked and operated, and what the consequences were for the life at the time, and also what it can tell us about constraining what might happen in the future, if anything. So that's what I'll be aiming to do over the next sort of 30 or 40 minutes. And so as Ray mentioned, you know, COP26 is on at present. So it's sort of quite, it's in people's minds in terms of, we know that environmental change is happening today. It's happening in lots of different places in lots of different ways, and it's manifest, you know, regardless of where you are on the planet or who you are, you see some representation of this environmental change. And of course, when we think about where we're, you know, the trajectory is that those changes are going to increase in particularly things like extreme weather, in frequency, in magnitude as we go forward. And so really trying to understand what might happen is really quite critical. And as Earth scientists, we know that the Earth system is an extremely connected one. The various components, whether it's the atmosphere, the lithosphere, the biosphere, the geosphere, they all interact with one another, which is why, you know, making small changes can have knock-on effects beyond those that you envisage, because the system is so interconnected. So for example, by increasing the CO2, which is what we're doing today, we alter temperature. Fundamentally, temperature is a master climate variable that knocks on to impact everything from hydrological cycling, atmospheric dynamics, wind patterns, you know, which then has subsequent, you know, vegetation patterns impacting albedo, ice sheet distribution. So one thing can have lots of knock-on effects. As we think about predicting the future, there are a couple of ways we might go about doing that. Obviously, the future is very data poor, so we might use models to try and predict how climate and the different components of the climate system might change in the future. But obviously, those models are only as good as the data and your understanding of the climate system that goes into them. And also, it's very hard to test how good those predictions might be. So another route by which we might understand what might happen in future, or provide constraints and a test bed for climate models, is to look to the past. So looking into the geological record. Okay. And so this brings us to looking at past high CO2 worlds. As of this month, CO2 in the atmosphere recorded at the Mauna Loa Observatory was around 415 parts per million by volume. And I've got time here that's going to be on the x-axis, and CO2 is on the y-axis. And I'm going to focus on CO2 because, as I said, it is a powerful greenhouse gas, and we have good proxies for it in the geological record, and a good understanding of its relationship with climate, generally speaking. So that's where we are today. And if we look back through the historical record, so this is the instrumental record from Mauna Loa, you can see that, you know, obviously CO2 today is higher than it has been since the 1950s when that record began. If we want to look back further in time to understand the different climate variables such as CO2, we can potentially go to things like ice cores or sediment cores. And ice cores are extremely useful for reconstructing past atmospheric CO2 levels, because tiny bubbles of gas can be trapped within the ice, and we can directly sample and measure that. By looking at ice cores, which, you know, the oldest ice cores are up to around 2 million years maximum, most are much, much younger, we can understand how atmospheric CO2 through this direct sampling has changed through time and across glacial interglacial cycles. So we see over that period, back to around sort of 2 million years ago, we're talking about changes between about 180 and 280 ppm, so much lower again than today. And indeed, if we want to find an interval of time with comparable CO2 levels to today, but also to those that are predicted under multiple RC scenarios for future emissions. If we take, in this case, I'm going to show the worst case scenario, hopefully, the 2100, which is that dashed horizontal line, you can see that we might be expecting CO2 levels as high as perhaps 1000 ppm by 2100 under a business as usual scenario. And so to get to levels that high, you're really going back in time to the Eocene, more than 34 million years ago. And obviously, the further back in time, we don't have instrumental records, we don't have direct records from ice cores. We're really looking at utilising the sedimentary record and the fossil record to reconstruct different environmental parameters, and in particular something called proxies. So we're using those different aspects of sediment chemistry or composition or fossils to provide, they indirectly record changes in the environmental parameter of interest, in this case CO2, that we can then measure to reconstruct CO2. So the Eocene, as I said, is really sort of one of the most recent past high CO2 world, and the one that I'll focus on for most of this talk. So the two sort of motivations that I have, or that we have as scientists for studying these past high CO2 worlds, are to understand how these much higher CO2 worlds looked and how they operated, and what lessons that we might take from these. And then, as I said earlier, to really use, by generating very high quality data sets in terms of both spatial coverage, but also in terms of our confidence of these records, use them as a test bed for Earth system climate models to understand how good they are at predicting outside of their training sets. Because of course, most modern models will be trained on the historical instrumental data sets. And so they haven't really seen anything, you know, when you're going into the future and it's going to be very different to what they've seen before, actually testing them outside of that training set is really, really key. And I'll come back to this project known as DEEPMIP, which is one that actually explicitly aims to bring together data and model scientists to try and tackle this question of actually how can we use past high CO2 worlds to constrain and test Earth system models that are used in various routes for policy information, as well as understanding how the Earth system works. There are multiple routes by which we can get at these fossil and sediment records to reconstruct past climate. And arguably one of the most powerful archives that we have is from the deep sea sediments that can be recovered from beneath the sea floor. And I'm going to introduce you to scientific ocean drilling. And this is a really nice and hugely successful project in terms of, in the sort of late 1950s or so, a lot of scientists, particularly in the US, were becoming quite frustrated by the grant proposals that they saw coming through the system at the time about what people wanted to research. And this was the time of the space race. And they wanted to get people as excited about exploring the deep ocean and its potential as they were about exploring, you know, outer space and the moon. And so this is how scientific ocean drilling for scientific research purposes really got going. And the way in which they decided to enthuse people to want to fund, importantly, but also go and explore the deep sea, was Project MOHOLE. So this is a group of US-based scientists in the late 1950s, early 1960s that put together this idea that they would try and drill to the crust mantle boundary, or the MOHO. And the idea was that they would do this because it was, exceptionally ambitious. They could get the public behind them, but also that it was it would provide an avenue for testing the new theory of plate tectonics. And one of the proponents, Harry Hess, is shown in the image here. And what they rapidly realized was that if you want to get to the MOHO, the easiest way to do it is to drill not through the continent, where you have to, first of all, drill through sort of, 10 to 30 kilometers of crust to get to that boundary, but to go to the ocean where the crust is much thinner, perhaps only a few kilometers. So it's much more achievable. And overlying that crust is a sequence of sediments of variable thickness. At the time, actually, this was quite ambitious in scope, because in order to drill into the ocean crust, you needed the ability to remain in one place for a long period of time. So actually, in order to achieve this, there were a number of technological innovations that had to happen, including the development of dynamic positioning as a system. So something that we routinely find on boats today was developed as part of the objective to drill, get to the MOHO. So in the first, so that was the plan: go drill MOHO, test plate tectonics, required significant investment and technological development in order to even sort of think about going to do it. The first cruise went out in the early 1960s, 1961, off the coast of Mexico in the Pacific Ocean. And on board this expedition was a series of photographers, but also John Steinbeck, the author, who subsequently wrote a piece in Life magazine about the experience, because this program did manage to capture the scientific and public imagination at the time in its scope and ambition about what this might tell us. Unfortunately, the project was ultimately unsuccessful in terms of reaching the MOHO, and actually it's something, the MOHO, sorry, and it's an objective that we still haven't achieved today, although we have drilled several kilometers into ocean crust. But what it did do was it showed that you could successfully recover large continuous sequences of deep sea sediments that were overlaying that crust, and actually that these contained extremely sort of high resolution and powerful archives for reconstructing past environmental and evolutionary changes. And actually, really, with the advent of this program, we saw the sort of birth of paleoceanography and paleoclimatology as we know them today. And what's really nice about this is that, so I should say at that time they only got, I think they drilled 13 meters into basalt, so they really didn't get very far into the ocean crust, unfortunately. But what's really nice about this is that 50 years later, or I think it's 52 years now, the scientific ocean drilling program morphed, and it's now the International Ocean Discovery Program. There's more than 25 member countries, and it's been sort of going in various guises, sort of exploring the deep sea and recovering sediments or the deep biosphere in various formats since then. And so it's one of the longest running and most successful international collaborations ever, and is still going today. And actually, earth sciences as we teach it today, and most of what, well, not most, but a lot of what we know about certain fields is heavily informed by this program, and it wouldn't look the same without it. And that's not just the plate tectonics in terms of they didn't get to the MOHO, but they did manage to generate different types of data that helped inform plate tectonic theory and how and where continents broke up. But also much more broadly, as I was saying, they allowed the discovery of deep microbial systems, paleoclimate events through time, and the relationship between CO2 and temperature, hydrothermal systems, sea level and ice cap dynamics through time, and also they helped refine significantly the geological timescale, something that any geologist needs and uses in order to sort of operate. So it's been a really crucial program for earth sciences. And I'll be focusing on what those sediments that were recovered from above the crust can really tell us about paleoclimates. And so those sediments, the most useful for the climate work that I do, and actually, I guess, sort of generally based on the proxy systems that we currently have, are the calcareous sediments that accumulate on the seafloor. And they're made up of the remains of two different types, primarily of microorganisms, the first of which are coccolithophores. And these coccolithophores are absolutely tiny. So they're, an example of those is shown in the inset image here. They're, maybe a few microns in diameter, but they can be so numerous in the ocean at certain times that they can be viewed from space in terms of their blooms. And that's what you can see in that background image here. That was from June 2020. You can see a bloom of coccolithophores of a modern species, Emiliania huxleyi there. So you can see that, volumetrically, these can be pretty significant. And when they die, so these are, I should say, coccolithophores are calcareous algae. They precipitate calcareous liths that are housed around an organic cell. And when they die, that sort of covering becomes disarticulated and sinks through the water column to accumulate on the sea floor. And actually it's things like the White Cliffs of Dover that are created almost entirely by these microscopic organisms. So despite their diminutive size, they can have a very significant effect in terms of being rock forming groups. They also play a very strong role in climate regulation themselves. So in addition to the calcareous nanofossils, the other group that we frequently find making up these calcareous sediments are the foraminifera. So these are not algae like the coccolithophores. These are so in this case, the planktic foraminifera. So these are zooplankton, and they have I'm showing here the shells that are left behind without the organic cells. So these are fossil shells, and you can see they have these glorious range of really ornamental shapes and sizes and features. But what's really great about foraminifera is that when they precipitate that calcareous shell, they capture the chemical composition of their shell provides a record of the environment from which they grew. And so by measuring the chemical composition and different elements or different isotopes that are preserved in the shell tell us different things, we can get at, how big were ice sheets in the past, how much atmospheric CO2 was in the atmosphere, how hot were the oceans where the foram was living and precipitating its shell. And coccolithophores are also useful in different ways, but it's foraminifera that I'll really focus on for the bulk of the talk. So if we start stepping back through time now, this is a map showing modern geography and continental configuration. And you'll notice that obviously we have the ice sheets on Antarctica and on Greenland in the northern and southern hemispheres. And if we have a look at how different the world was in the Paleocene and the Eocene, so going back between 34 and 65 million years ago, an interval we know to be a high CO2 world based on our proxy records, you can see that the world was very different. We don't see significant ice sheets on either hemisphere. Also, you'll notice that the Southern Ocean, South America and Australia are very close to Antarctica. There's not a through flow. So the Antarctic circumpolar current that we have today, where we have this large open gateways that allow this current to develop, which is a key part of our climate and ocean system, it didn't exist in the Paleocene and the certainly the earliest Eocene, because there wasn't that open passage around Antarctica. You'll notice there was also the Tethyan Ocean, which was to become the Mediterranean much later on. And The Panama Isthmus was open as well. So North and South America were not connected to one another. And also, India had not yet collided with Asia to form the Himalayas. So the world did look very different at this time, but there are still things that we can learn if we take account of that difference in paleogeography. And as I mentioned, there were no ice sheets on the poles, but what we did see, so actually if you went up to the modern Arctic today, the background image is what you would experience if you went up today, whereas the inset photo is what it would have looked like around 50 million years ago. So a warm, humid swamp, something like that. And indeed, we find fossils of organisms such as crocodiles, things that we would associate with relatively warm temperatures today in those areas, indicating they must have been warmer in the past. So the Eocene, as I said, so was warmer than it is than the world today. And actually this figure really nicely contextualizes that. So on the x-axis, we have time going from young on the right to old on the left. That's my left and right, that is. And then on the y-axis, we have average global surface temperature difference relative to 1961 to 1990. So basically, how much warmer or colder was it than between 1961 and 1990? And it's color-coded with temperature. So blue colors indicate cool, and red colors indicate warmer. And the basis for this record is the deeper time part, at least, is foraminifera in themselves, but those that live on the seafloor rather than in the surface ocean. As you go back through time, what you'll notice is that temperature increases through the Cenozoic, and the warmest interval of the entire Cenozoic is back in the early Eocene. So from 56 to around 47 million years ago. And often this is termed an Eocene hothouse because of the warm climate that characterized that environment. And the event that I'm going to talk about specifically is known as the Paleocene-Eocene thermal maximum. So this event occurred at the boundary between the Paleocene, where it defines the boundary between the Paleocene and the Eocene. It occurred around 56 million years ago. And it's the largest and most abrupt of the global warming events that have happened over the last 65 million years. And it's often thought to be the best analogue that we have for understanding what happens when you put a lot of carbon very quickly into the ocean atmosphere system. And so a huge amount of research has gone into understanding this event over the last sort of couple of decades. So going to a bit more depth on the PETM itself, you see the figure on the left-hand side here shows at the bottom is a sediment core lying horizontally. So this shows a change from white sediment in the older portion, around 55.05 million years, becoming darker and then lighter again. So this reflects the amount of carbonate in the deep ocean. So associated with the Paleocene-Eocene thermal maximum, there was a huge addition of isotopically light carbon to the ocean atmosphere system that ultimately resulted in large-scale global warming. The input of carbon happened very, very quickly on geological timescales, probably less than 3,000 years. And associated with that in the sedimentary record of the deep ocean, at least, we see this change in sediment character because of the acidification of the deep ocean. And so we see a reduction in carbonate being preserved and an increase in the amount of clay being preserved during the PETM itself. The record above that is the carbon isotope record. And you don't really need to focus on the details of this. It's just to say that there is this large shift in carbon isotopes that are preserved in, basically, in this case, in carbonates. But actually, anywhere you look on the planet generally, and you can, any archive where you can reconstruct carbon isotopes, you will also see this large, abrupt, negative carbon isotope signature. That actually is a really key defining characteristic. And that this is what tells us that there was a large input of carbon to the system at this time. So the PETM is known from sort of more than 100 sites now, so it really was global in terms of its scale. And the ultimate driver of this event and where the carbon came from, sort of, if I'd been giving this talk even sort of 5-6 years ago, my answer probably would have been different. For a long time, it was thought, you know, a lot of suggestions for where that carbon could have come from, like how do you get carbon to drive that warming so quickly into the system? And, you know, methane hydrates for a long time was really the dominant hypothesis. So these ice crystals housing little methane molecules that are often found on the continental shelves. The idea was that if the ocean warmed a little bit, then you get a massive release of methane into the atmosphere, driving global warming. That may still have been involved, but actually the dominant driver seems to be, based on most recent work, there's increasing evidence that warming and the addition of carbon was driven primarily or initially by the North Atlantic igneous province. So the Giant's Causeway is sort of a similar time interval in this late Paleocene, early Eocene. So there was a huge amount of volcanic material injected into sediments at this time, resulting in the generation of methane that was then released into the atmosphere. So while the PETM 56 million years ago, ecosystems did look a little bit different, the continental geographies were a little bit different, actually it's used as an analogue, and actually is quite effective as an analogue, because we do see similar types and magnitudes in some respects, but certainly directions of environmental response to those being seen today. So part of the project that I was involved with, as I said at the beginning, was this DEEPMIP project, so the Deep Time Model Into Comparison project. And so this brought together data scientists like myself with modelers to try and ultimately generate better understanding of how the climate system worked in the past and may work in the future. And as part of that, we focused on certain time intervals for which we thought we could get a lot of temperature and CO2 data from intervals where we saw abrupt environmental change. So the PETM was one of the key targets for this work. And we pulled together all of the temperature records that have been generated over sort of the past 30, 40 years from both land and the oceans. So comprising more than 60 sites. These were quality controlled, they were all updated, and temperatures calculated using the latest techniques. And we ultimately ended up with 60 different locations with more than 2,000 data points. So we were able to get this really quite rich idea of how temperature and CO2 changed and across from the late Paleocene and across the Paleocene Eocene thermal maximum by utilising different archives. And the deep sea archives provide a key role in that. So I should say that there are a lot more temperature records than there are CO2 records. We've had temperature proxies for a lot longer. They're a lot easier to measure. They're a lot cheaper to measure. And so the majority of the records that we have are temperature, but we do have a few high quality CO2 records now too. But obviously temperature is much more spatially variable than CO2, generally speaking. So going through the results of that project, after we'd done this large data synthesis project that brought together, it was a huge international effort. The sort of main output from the temperature side is shown here. So what you can see are individual dots of, in this case, sites that passed a high quality check, and they're color coded by the temperature relative to pre-industrial. So pre-industrial being sort of 1850 to 1900 in this case. And so this is the difference from the PETM to, which is the peak warming within the Paleocene thermal maximum compared to pre-industrial conditions. And I guess the first thing you notice when you look at this map and the interpolation that fills the space between the sites, which are the small filled circles, is a model prediction, a low quality model prediction. This is not a high quality numerical model at this point. With the first thing you'll notice that all of the colors are in this pink, yellow, orange, red spectrum. So indicating that basically everywhere we have records, and our predictions are that everywhere on the planet was warmer in the Paleocene-Eocene thermal maximum than it is today. And actually, some places were a lot warmer. So warming was not equal everywhere. You see much less warming in the sort of subtropical gyres, those yellow-orange areas of the Pacific and Atlantic, compared to the high latitudes, where you might get sort of 20 to 24 degrees hotter in terms of the poles. And so those are sort of key observations, really, that the global temperature was much warmer in the PETM than today, but that temperature warming wasn't distributed evenly. We see this artifact like we do today called polar amplification, where we see more warming at the poles than anywhere else. So then the question really is, okay, so we know what the temperature profile looked like and how temperature changed across the world. We can work out the global mean surface temperature. So if you sort of average out all those values, it was about 32 degrees. And we can then compare that to how much CO2 was present at the time in the atmosphere in order to understand the relationship between temperature and CO2. And that's what's in that left-hand panel here. You can see that in the top right, there's a red dot showing the PETM had high CO2, probably somewhere around 1800 ppm compared to our 400 today, with a global mean surface temperature around 32. You can take the pre-PETM value of the late Paleocene, which is obviously a little cooler because it's before the warming. And you can also put on other climate events so that you can start to understand through geological time the nature of that relationship. And so here you can see the pre-industrial values have been put on. So it's around 280 ppm and a global mean surface temperature around 14 degrees. The Pliocene, which was warmer at certain times than today. And then, of course, the LGMs, the last glacial maximum, which is actually colder than today in pre-industrial conditions, the last time in which we had significant ice sheets in both the northern and the southern hemispheres. So northern hemisphere not just being Greenland, but also across North America and Eurasia. And you can see that there is this positive relationship between those two variables. So the geological record sort of supports the idea that CO2 and temperature are related to one another. And actually what's really great is that once you have these two parameters, you have reconstructions of temperature in terms of the global mean average, and you have the atmospheric CO2, you can get at a key variable known as equilibrium climate sensitivity. And this is essentially one number that describes the entire response of the Earth system. And it's a really key number because it's a key parameter in most, well, no, not most, all climate models. And it describes the relationship or the amount of global mean temperature change you get relative to a doubling of CO2 once the system's reached equilibrium. So what that means is that it's that the relationship after all of the different feedbacks within the system have played out. So, there's been equilibrium of changes in vegetation, ice sheet dynamics, all of that. So you can only understand this over geological timescales. It's not something you can look at over 10 years, for example, because all of those really critical components of the climate system don't operate and equilibrate over those really short timescales. So anyway, looking at the fossil record gives us these two parameters. And what that ultimately allowed us to do was to figure out the ECS for these different intervals of the hothouse during PETM and during the late Paleocene. So in that lower right-hand figure with the wiggles, what you can see on the lower x-axis is a value of equilibrium climate sensitivity. And on the left is the probability of that being correct, of that value. The grey vertical bar shows you the range of values for ECS that were predicted and utilised in the last IPCC report back in 2014. So you can see there's quite a big range of values that were utilised. And because this is such a fundamental parameter, and as we spoke about earlier, temperature is a master climate variable, it impacts so many other parameters, from water vapor formation, cloud dynamics, wind patterns, that actually that creates a lot of uncertainty in any few other sort of knock-on predictions that you make. The good news is that the geological predictions have helped to play a role alongside other sort of model refinements, modern observations of various kinds, that ultimately allow us to get back down to a much narrower range of temperatures, ECS values. So suggesting that probably the equilibrium climate sensitivity, we're talking about 2.9 to about 2.6 to 3.9 degrees per doubling of CO2. And as I said, the geological record was a key part in helping to constrain that and provide increased confidence of the range of values we should be inputting into those climate models. And so having a direct impact into policy. So that's how the data and the data has been utilised to create this key value that can then feed into models. But obviously the models can also be tested against the data so that you can ultimately see where the weaknesses of one or the other might be. And so that was the next couple of slides that I'm just going to talk about, is that same data set that we utilised, the database of PETM values for temperature and CO2. A series of different models were run, different climate models, and there's I think 8 that are with all the series of names in the vertical part of the table here. They will run at different CO2 concentrations, and one of the key fields that's always output in these models is temperature. Again, it's another reason for us to, it's a handy coincidence, this is one of the key ones that we can measure in the geological record as well. And what's really nice about this is that when you look at the realistic range of CO2 levels, we're now at a point very different to where we were 10, 15 years ago, where we get really good agreement, first between different climate models, but also between the data and the models. And so what you'll notice here is that these are 6, each panel is a different climate model output for the difference in temperature between the PETM and pre-industrial conditions. So again, with those yellow, orange and reds being warmer temperatures. So just as with the data, you'll note that everything is warmer than pre-industrial conditions, which is great, and that the majority of the models have this really well-developed polar amplification present, which was a really big problem for a long time, trying to get that polar amplification represented in climate models. Yet we have multiple lines of geological evidence that it was present. So this is really great. You're starting to get really consistent patterns. There are small scale differences, but globally, and actually even sort of slightly smaller scale than that, we're getting good agreement. One area that you'll notice that there is significant disagreement still, and that actually is the focus of a lot of ongoing work, is trying to sort out what's happening down in Southwest Pacific. Those red dots, as with some of the earlier plots, show the data that we have. And then obviously the interpolation behind is the model. And you'll see that the data are red and everything behind it is yellow or orange. So the Southwest Pacific, the data is suggesting, was much hotter than the models are predicting. And so now the case is going back and looking at, is that a model problem or is that a data problem? So both communities working independently and then sort of comparing to try and get the best constraints on those. My final couple of slides that I'll talk about are actually going to the fossils themselves rather than the chemistry and the geochemical records and environmental parameters that we can generate from them. And so I'm going to specifically focus on the marine realm. So the PETM, obviously, as we've said, significant global warming event. We see something like 5 to 8 degrees of global warming within those less than 3,000 years, but obviously with different amounts in different places. And there was a profound impact on the life at the time, whether you were on land or in the oceans. In the oceans, we saw a range of responses. We saw changes in the abundance and diversity of basically every group of organisms that lived at the time, from the micro through to the macro, where we have good enough records to tell anyway. Amongst amongst multiple groups of plankton, including the planktic foraminifera, we saw new species arising in response to this global warming event. We saw large amounts of migration where tropical and subtropical species were able to expand their range as temperatures increased and the higher latitudes became more habitable for them. Of course, that causes subsequent pinching out at high latitudes for those organisms living in those environments. We saw dwarfing in many groups for a variety of reasons, but in essence, because of stress. So planktic foraminifera again do this. We also see it in the ancestral horses in North America. They get smaller during the PETM and then become larger again afterwards. We see some incidents possibly of malformation, so it being harder to make shells or organisms precipitating thinner calcareous shells in response to ocean acidification and temperature stresses. And we also see things like bleaching. So where we are able to reconstruct it in the record, just like you see with corals today, where algal photosymbionts create those beautiful colours on the corals, actually some groups of organisms, in particular planktic foraminifera, hosted, many species hosted algal photosymbionts that were an important part of their ecology. And what we find is that that relationship breaks down during extreme warming, at least temporarily, sometimes with long-term consequences, and others it's just a temporary situation. So lots of different types of biological responses, but we didn't really, in the surface ocean at least, see any widespread extinctions, and certainly not a mass extinction. The seafloor is a different story, actually. So during the PETM, we actually see the most significant extinction of benthic foraminifera from the last 90 million years. It depends where you are as to how extreme that extinction appears, but you can see in that red and blue panel, as you go up through geological time, from oldest at the bottom to youngest at the top, we see the red is number of species, so we see a precipitous drop in the number of species associated with the onset of the PETM, and that darker sediment comes in. And actually the size of the benthic foraminifera images that are shown also indicates there's a dwarfing of those species that do survive the boundary. And then moving across onto the right-hand side, these black and white images, these are cross-sections through sediments taken from coastal sections, looking at bioturbation. So this is representative of the soft-bodied organisms that we're not finding typically, so things like polychaetes and worms, that usually would be moving through the sediment, moving oxygen and nutrients. But actually what you'll notice is that before and after the PETM, there's lots of black and white streaks in the sediment, so there's happy bioturbation happening. During the event itself, during peak temperatures, we see very little of that bioturbation. The sediments in fact look very white. There's no evidence of extensive burrowing. And this was probably a combined effect of increased temperatures and resulting decreased oxygen concentrations, but also there might have been other factors coming in as well. But fundamentally, the seafloor was a very different place to the surface ocean at this time in terms of how it responded. So for my final slide, just sort of summarize really some of the lessons that I think we can take. And it's that the geological record actually, is full of natural climate experiments of different kinds. Not all of them are perfect or good analogues for what's happening today, but actually by studying the range of how the climate and environment change and how organisms change across different types and magnitudes of events allows us to really understand the full scope of how the Earth system responds. And actually there are kind of useful relationships in there that do then subsequently provide us with predictive power. The rate of anthropogenic change that we see today in terms of temperature and the CO2 change is unprecedented in the geological record, with the exception of meteorite impacts such as the KPG, the Cretaceous Paleogene boundary around 66 million years ago. But still, as I said, the PTM, it's one of the fastest events that we have to study, but it is slower in terms of the environmental change than what we're happening today. So we might expect that actually that's going to have a significant impact on the types of impacts that we see in terms of how extreme they are, particularly for life, whether or not, you know, the change is happening within evolutionary timescales. So past events can be really useful for telling us about, you know, getting at the reality of how complex the Earth system really is, things that can be difficult to parameterize without that information, and can provide us some key information on the types and directions of environmental or biological changes. And if anyone wants to find out more, there's a really great article published by the Geological Society led by Carrie Lear that was published last year that sort of goes through in a lot more detail about how we can use the geological record to tell us information about our current and future climate. So thank you very much.
Okay, wow. Well, thank you very